Here we go. Okay. Welcome, folks. Friday evening. I'll start with a recap of what we did in our previous session. It'll be very brief. And then I shall leave the floor to Sirisha to take over. She'll take us through the ID3 algorithm. And we have Kayal Viri, who shall demonstrate the same through a Python code. So that's the agenda for today. I shall share my screen now. Are you able to see my screen?
Yes, Rishi.
All right. Briefly, I'm not going to go through all this again. We did this. Should anyone, I don't know whether I shared it in the Telegram group. Maybe I didn't. But should anyone need it, I'm more than happy to share it. But the fundamental principle is we are trying to define what is called as information. And then we measure information through what is called as entropy. And we have some sense of what information and entropy is. It's a measure of randomness. So which means if it's more of the same, then we know that the entropy is low. If it's, say, if you're dealing with something very different, and I mean, a lot of different things, but in equal proportions, then probably the entropy, I mean, you're dealing with very high entropy. So we understand that. And what we also understand is when we use any attribute to split the data, it's extremely important that the attribute splits the data in such a way that the distribution changes. If the distribution of data doesn't change, when I say data here, we're dealing with classes because that's our concern. So if you look at this case, you had 3 classes here, C1, C2, C3. There was certain distribution. The attribute A, which took 2 values, A1 and A2s, split. It split the data. And if it just so turns out that this distribution is exactly the same as the original distribution, then this attribute is practically useless. Because the whole idea of doing the split is to get to a different distribution so that you can reduce the entropy. That's the whole idea. All right. And that's the basic principle. But I'm going to ask one question, and I'll stop with that, of course, after getting an answer. And the question is as follows. So let's say hypothetically, I'm going to put some numbers here. So let me first copy this so that I'm just going to copy this on a different worksheet. All right, sorry, give me a moment, folks. Okay. Now, instead of the attribute A splitting this data equally, let us say hypothetically, it managed to split the data the following way. There were 10 instances that moved into A is equal to A1. And let's say there were 6 instances that moved into A is equal to A2. And let's say this entropy, I want to keep it simple, were to be 1.5. And let's say this entropy were to be 1.1. The question that I have, and I don't want the usual suspects to answer this question. So when I say usual suspects, the Sirishas and the Abhinavs and the Kyle Viris and the Sandhyas of the world, I want someone else to answer this. What would be the average entropy after the split? Before somebody answers, Of course, Yasholeka is also part of the usual suspects, so someone else. Before someone answers, just raise your voice so that I know who's answering. I'll decide whether to let them answer or not. Anyone, folks, give it a shot. So who's it going away? Give it a shot, folks. Others. If you didn't understand the question, so these are the key elements here. I'll just highlight it. This is important. This is important. And this is important. Nothing else matters. All right. The rest is all paraphernalia. So don't really worry about them. Anyone?
We see Sabrishan here.
Sabrishan, you're too smart. Nope. Someone else. I know you will crack it. Let me see if somebody volunteers. If nobody volunteers, then I'll come to you, Sabri. All right.
Sure, we see.
That doesn't mean others aren't smart. There are a lot of smart people. It's just that people don't apply their intelligence. Anyway, so I'm just waiting for somebody to volunteer. The 22 on this call. Come on, folks, just take a shot. Okay, I'm going to stay silent.
Is it 1.3?
Who's that?
Madhumita.
Sorry?
Madhumita.
Madhumita. All right. So help me understand, how did you arrive at that number?
I calculated the probability of this A1 10 by 16 into.
Okay, so this is 10 by 16. So, so which means out of 16 instances, 10 is going to go to A1. All right. And then?
This is 6 by 16.
Okay, wonderful. And then?
And multiplied 0.65.
Okay. Yeah. By what?
5.
0.65 by?
0.65.
Mm-hmm.
Multiplied it with the entropy of A1.
Okay, very good. And then?
And multiplied 0.35 with the entropy of A2.
All right.
Summed it.
Okay, so correct me if I'm wrong. So what you did was, you took this number, multiplied it by its entropy. Then you took this number, multiplied it by this entropy, and then you summed up. Correct? Am I right?
Yes, yes.
Okay. Sabarishan, would your approach, I mean, had you answered this question, would you have a different approach or would you have the same approach?
Same approach, we see.
Okay, both of you are right. Good job, folks. Yes, that's right. So the idea is simple. Here is a bunch of data, 16 data points. So just imagine the tree, folks. 10 out of the 16 moves into this branch, 6 out of the 16 moves into this branch. And if you take this particular branch, I mean, we're calculating the weights or, probabilities. Both are similar here. So as Madhumita said, this is nothing but 10 by 16. This is 6 by 16. And then you have the entropy of each branch, 1.5 and 1.1. So what you're going to do is you're just going to multiply the probability or the weight with, Both are similar here. And the entropy, which is this, then this probability multiplied by this entropy is this, and then you sum it up. That's your average entropy after the split. All right. Of course, I haven't asked the question on information gain. That's very trivial. We know that. The information gain would be the entropy prior to the split. And you take the entropy after the split, and then you subtract the two. All right. Okay, good. Anyone else who hasn't understood this? Because it's extremely, extremely important. The whole ID3 algorithm rests on this idea that that we were discussing now. So anybody who hasn't understood this?
We see it's Ratna Bhupati.
Yep.
Have you assigned those values, like assume the 10 and 6, or are those assumptions, or
Yeah, that's assumption.
because in the
Just for the sake of
okay.
yeah, it's assumption, not this. This was
Okay.
in our initial example. I made it very, very trivial by making it 8 and 8, right? So
Okay.
Sometimes when you do that, you don't appreciate what's happening behind the scenes, which is why I said, let's assume hypothetically that this were to be 10 and this were to be 6.
Okay.
All right. Anyone else who hasn't understood what's happening here? Okay, I shall take that as a yes, that everyone has understood. So what I shall do is I shall now leave the floor for Sirisha to take us through the ID3 algorithm. Sirisha, over to you. I think I should share screen. Yeah. Go ahead, Sirisha.
Hi all. Now let us understand how this ID3 algorithm works, okay? So ID3 basically works on the same principle like which we have already discussed. I mean, this has these two approaches. One is top-down approach and the other one is greedy. Top-down greedy approach is what it uses. Top-down means we will start building from the root node to the leaves. And after that, greedy approach means every step we'll try to find out which is the optimized or the best path, and we will best feature, and we will use that feature as the root node. Okay. Now let us take this example and we'll understand
Okay,
more.
can I just one moment?
Okay.
Not a question for you, but for the audience. What do we mean by greedy? Top down, I think all of us understand. So this question of greedy did come up in the previous session, but what is your understanding of greedy? I leave this question for anyone to answer. So just feel free to answer, folks. It's open to all.
In the greedy, we will be checking all the possible outcomes and choose the best one.
That is
at
right.
the current moment, and we will not be worrying about the future.
Okay, that's right. So when you say future, what do you mean in this context?
In the further levels, when we are going down the other nodes, we will not worry whether this current decision would be best in the next level.
Okay, so what you're saying is, I take a decision at a node. I'm extremely greedy about my decision. Of course, when I go to the next step, when the algorithm goes to the next step, I mean, the algorithm has multiple steps after I've taken a decision. But then, if I understand what you're trying to say, you're saying that at a particular juncture, I don't care about what's going to happen later, right? I just care about maximizing my greed at that point. Is that what you're attempting to say?
Yes, we see.
All right, fair point. So I'll give an example from social life. Just imagine, folks, there is a plot besides your residence, an open plot. So you have trash at your home. Of course, there are houses around that open plot. So all of us know that all of us are greedy And we all know that in a matter of time, that open plot will be filled with trash. Why? Because each household around that open plot is a greedy house. It's easy for them to just throw trash into that open plot rather than walking, say, 200 meters and putting the trash into the trash bin. Now, just imagine. In this particular case, we dispose of the trash using a greedy algorithm, each household. But if you think about the overall scheme of things, is that a really a good algorithm that works well for all of us? Certainly not, right? So that's from social life. This is also true for an algorithm such as ID3, where you adopt a greedy approach at a juncture, but that doesn't mean that's the best decision tree. The follow-up question would be, why adopt a greedy approach? Anyone? Think about it. Why adopt greedy? Why can't I be generous? I mean, in the sense, why can't I
Save your
think of,
efforts.
okay, that who was that?
Oh, yes.
That's right, saves my effort. That's right. So if you think about it, if you think of all possible decision trees, it's not just lazy. The way to look at it is, if you think of, given the data that you have, and if you think of all possible decision trees, you will have so many combinations that it will be impossible. I shouldn't use the word impossible, but it will be very, very costly for an algorithm to look at all possible decision trees and then figure out, this is the most optimum tree. So we avoid such algorithms because we want to solve problems reasonably well with reasonable accuracy. So which is why we adopt algorithms such as, one that is greasy. I mean, ones are not greasy, greedy. I'm sorry. And it works well, apparently. So that's the reason why we take this route. Sirisha, over to you.
Okay. So this is the algorithm, and I mean, this entire algorithm is based on choosing the right classifier. Right classifier is choosing the right node. Okay, and to choose this node, right, we depend on entropy and information gain. We basing on the value of entropy and information gain, we will be choosing the best classifier. Okay. Entropy is nothing but it's the measure of impurity or uncertainty in the data. Okay. And we already have a lot of discussions on this, right? So, and the formula to find entropy is minus p plus log base 2 p plus minus p minus log p negative base 2. This means probability of getting a negative value into log times the probability of getting all the negatives base 2. Similarly, this is probability of all the positive values.
Question, Sirisha.
Yeah.
Why? So when you say this is the, okay, why we're looking at only two values of p plus and p minus?
I mean, here actually, as per, if we consider, in this example, right, if I see it has only two outputs, either it is yes or no.
Right.
Where,
so had it been, say, because this is a binary,
yeah, binary classification.
classifier. Yeah. Okay.
Yeah. Since
But
it
had
is
it been, say, hypothetically, had it been, say, three different
then we will have one
classifiers.
more one more probability into log times of probability. Actually, this is sigma.
Correct. Okay. So
Yeah.
basically what we're saying is sigma times negative P log P, of course,
Yeah.
to the base 2, right? Where P
Yeah.
is the probability of a particular class. Is that right?
Correct.
All right. So
Probability
here,
of output classifier.
yeah. So here it is positive and negative because there are only two
Outcomes.
outcomes. So you call one positive, the other one negative. All right.
Yeah.
But if there are
Yeah.
multiple classes to which, I mean, classes into which we split, then of course you have multiple expressions, such expressions. So, okay.
Correct.
Okay. Thank you.
Now, if you see, right, I mean, this is the graph we have. This is the graph with the outcomes and entropy. If you see this, right, I mean, we have only one class here, like all the outputs belongs to negative class. And if you see this, right, all the outcomes belongs to positive class, like they belong to single class. In this case, what we have, I mean, the entropy will be 0. And the information, right, we know the complete information. We know that it belongs to whatever you take, right, you know that it belongs to this negative class only. Here, whatever you draw, right, you know that it belongs to positive class. So you know the actual information. There is no uncertainty in the data. This is where entropy is 0. Now, here if you see, right, I mean, I'm taking you through the entire graph. If you see this, right, there are two positives and others are negative here. Okay, 1, 2, 3, 4, 5, 6, 7, 8. Okay, so this is the place. Okay, this is where we have the entropy somewhere close to 0.7. And if you see this, right, there are equal number of positives and negatives. This is where we have lot of uncertainty, because here we don't know. Let's say if a basket has equal number of green balls and yellow balls, we don't know. If you try to take a ball, you don't know if you will pick a red ball or an yellow ball, right? Because they're equal in number. So in that case, completely the information is uncertain. In that case, right, we don't have proper information. That is where we will have maximum entropy. And here it is 1. Always, if you see this, right, I mean, if you see this, you know that it is certain it belongs to negative class. But here if you see this, right, chances of getting negative is more compared to positive. Okay, it's not completely uncertain, but we have some information. So that is where, I mean, there is entropy, there is uncertainty in the data, but yes, to a level. And that is, let's say it is 0.7 here. And the maximum entropy will be there when we have equal number of positives and negatives. Okay, I mean, not only positive and negative. Let's say if there are 3 classes, let's say multiplication is the 3rd class. Whenever they are equal, they are in equal number, right? That is where we will have more entropy, because we are not clear. We don't know what will come. What anything can happen in that case. So that is where we will have more entropy. So if you plot a graph, right, it just looks like this. Now, information gain. Information gain is the measure, okay? Measure of a measure basing on which we calculate features capability in the data set. Basing on that information gain, what happens? We can identify the feature which gives maximum, what is that, information. So what happens? Entropy will be reduced. We have to identify feature in such a way that the entropy will be reduced and we have maximum information out of that. And the other thing is information gain is a metric for entropy reduction. Okay, and this is brought by segmenting instances. We are dividing instances basing on the classes. That is where, I mean, we have already discussed, right? This is mostly applicable in categorical kind of data where we have limited outputs, limited classes. Okay, so that is where we use this information gain. This is nothing but I mean, the knowledge or the feature gives us certain information. Basing on that, we divide the, I mean, we use the node, or we use that feature as the node. Okay, now selecting the characteristic provides most information about the class. and it will help to achieve, it helps in maximizing our information gain. We have to choose attribute in such a way that, or the feature here, feature or attribute both are same. We have to choose feature in such a way that it gives maximum information gain. And this information gain, this is the formula, but actually, for our understanding purpose, what we can say is this is, if you see this, right, this is entropy after split, and this is average entropy before, sorry, this is entropy before split, and this is average entropy after split. The difference between these two gives information gain, and this information gain should be maximum. Our feature should be chosen in such a way that our information gain is maximum. Okay. Now, if you see this, right, this is the formula here. This is the, this is the entropy. Okay. The initial entropy before the split. And this is average information. This is nothing but the average entropy after split. And information gain is nothing but entropy before split minus entropy after split.
Sirisha, can you just go back?
Mhm.
So this, folks, the average information, don't be stumped by it. That's basically the stuff that, the example that we were discussing, the one that Madhumita had answered, this is precisely that. So we had the 10 by 16 and then followed by 6 by 16, and then we multiplied it by the entropy, right? So that's basically the average information that you are seeing on the screen. Sirisha, go ahead.
Okay. Now I'll take you to this example. Okay. So now this is the data we have. This is small data. Okay. It has just 14 entries. Okay. Here, what we are trying to do is we are trying to predict or make a decision tree that predicts whether tennis will be played or not on that particular day. Basing on this data, we should be able to predict if tennis will be played or not. And this is the data here. Now, our first step is we have to find out the root node. Okay, root node means the best classifier or the best attributor. Okay, which gives maximum information. That is what we have to classify. So, for example, right, let's say plus plus. Let's say I have 4 classes, okay, and I want to predict if it belongs to, let's say there are 4 colors: blue, yellow, red, white. Now let's say I want to draw a ball, okay, and I wanted to know which color ball I have picked up. So if that is the case, right, how can we make a decision first? We can create something like this. Let's say it belongs to blue and yellow or red and white as a first step. And as a next step, right, as a segregation, let's say from here, we will say that it belongs to blue yellow. Then in the next step, we can find out, right, if it belongs to blue class or yellow color. Similarly, see here, actually we have 4 colors. We don't know which color it is. And here, if you see, right, as a first step, we can construct tree in such a way that we have only 2 steps here. First step is we will verify if it belongs to blue yellow or red white. And the second step will be to find out if it belongs to, let's say if it belongs to blue yellow. Then from here we can find out if it is blue or yellow. And similarly, if it, let's say if it belongs to red white, we can find out if it is red color or white color. So within 2 steps, you will be able to find out the information. So the tree will be like this, very simple tree with 2 branches. That's all. You got it, or I confused you? I'm not sure.
Go ahead, Sarisha. Go ahead.
Okay. I'll go ahead with this, VC.
Please.
So that is how actually we choose the root node. Okay. Now for this data, I wanted to understand, or we will have to find out which should be the root node. Let's say if you see this data, right, we have outlook, temperature, humidity, windy. These are all features. Features are the attributes. And play tennis is the output variable. This is what we have to find out. If a person will play tennis on that particular day or not. This is target or output variable, and we have 4 features. Okay, out of these 4 features, any feature can be root node. So let us try to find out which will be the root node here. So first thing is basing on ID3 algorithm, right? If you see this data here, how many yes are there? 1, 2, 3, 4, 5, 6, 7, 8, 9. So total number of positives is yes. Positives means yes, a person will play tennis if these conditions are met. N is no, person will not play if under these conditions. So there are total of 14 instances, out of which 9 times it is positive and 5 times it is negative. Now we will have to calculate entropy of this data. So formula for entropy is this thing. I mean P log P, right? P is probability there. Okay. P log P in sigma P log P, out of which P is probability. Here what is the probability of positive here? Probability is 9 by 14 times log 9 by 14 base 2 minus 5 by 14 log 5 by 14 base 2. So this is total entropy. Okay.
Okay, this is entropy of what? 0.940 is the entropy of what?
Entropy of this whole data.
What do you mean by whole data?
I mean, out of when we consider all these attributes.
Is that so? Are we looking at outlook, temperature, humidity, windy
Yes.
when you're calculating this entropy?
Correct. Because
Are
we
we?
have considered all positive. Yes.
Do
Because
we
see
even
here,
care about outlook, temperature, humidity, and windy when you calculated this entropy?
no,
This
we are not.
entropy.
No, we are not actually looking at any of these attributes.
Correct.
Complete data, we have calculated entropy. Irrespective of all this.
Sorry, I didn't understand. Say that again.
Irrespective of features, right?
Uh-huh.
Basing on number of positives and negatives,
Of
we have
what?
calculated
Of what? Positives
of
and negatives of?
play tennis. I mean,
Exactly.
if the person will play or not.
So
Basing
which
on
means,
that information. Yeah.
So the point that we're trying to make is forget outlook, temperature, humidity, and windy. There are 14 days. I know that 9 days I'm going to play tennis. 5 days I'm not going to play tennis, right?
Mm.
I'm not bringing in outlook. I'm not bringing in temperature. I'm not bringing in humidity. I'm not bringing in the windy characteristics as well.
Mm.
By just going by this information that I have, I already have, I mean, I'm calculating an entropy, correct? So it is not technically the entropy of the data. It is the entropy of the target variable here, isn't it? In this case,
Yeah.
play tennis, right?
Yeah.
Okay. Now, question for you again, Sarisha. So what is the objective? So you've got the entropy now of the target, I mean, of play tennis. What is the next step? What are we trying to do from here?
Now I wanted to find out entropy of outlook, each of these features, and I wanted to see which feature will give maximum information gain.
So what we are trying to say is we have the entropy of play tennis 0.940. We are trying to use one of these attributes, one or more of these attributes, or rather one. Okay, since it's a decision tree, at any given point in time, you'll use only one attribute, correct? And see whether you can reduce the entropy, correct?
Yeah, and we have to find out attribute actually. That is our intention.
All right. So the attribute that will result in maximum information gain. which means the one that will reduce my entropy as much as possible. That's the
Correct.
attribute that you're looking for. Okay, go ahead.
Correct.
Yep, go ahead.
Now, see, we have 4 features, right? What we will do is we will find out entropy for each feature, for each of outlook, temperature, humidity, and windy. And we will see which attribute gives maximum information gain. Now, let's say if we look at outlook, right? This one. So outlook. So if you see this, right? Outlook has 3 attributes. Let me take you. See this one. Outlook. Outlook has 3 values: sunny, overcast, rainy. Okay. So for each of the attribute, right, we will find out where a person will play tennis or he will not play tennis basing on the given data. So this is how it is. We captured the information here. If you see this, right, whatever the value of overcast is, it is always yes. So that is also mentioned here. Okay. So basing on these values, right, we will try to find out entropy. Entropy whenever the outlook is sunny. Whenever it is sunny, we have 3 no's and 2 times a person will play. So if you calculate it, it is 2 by 5 times of log 2 by 5 minus 3 by 5 log 3 by 5, which is nothing but 0.971. Okay. Now, overcast. Overcast, right? There is no here. Okay. Person will always play tennis here. Okay. So the probability of playing tennis is 1. So 1 log 1 minus 0 log 0. Log 1 is 0. 0 times anything is 0. So we have 0 here, which means there is no entropy. Entropy is 0 because we are certain that whenever it is overcast, person will definitely play. We have good information here. So, okay, this is one thing. Now we'll try to find out, entropy whenever it is rainy. Whenever it is rainy, right, we have 3 yes and 2 no. So it is again the same, one and the same, like here 2 by 5, 2 by 5, 3 by 5, 3 by 5. Here again the entropy is 0.97. Okay. Now we have calculated entropy, individual entropy. Now we have to find out the information gain. Okay, because we are looking for the feature which gives maximum information gain. Okay, no. Actually, here we are considering only outlook. If you see this, right, we have considered only outlook feature. And inside outlook feature, we have these 3 values, basing on which we have calculated entropy. Now I wanted to calculate information entropy, or what will be the entropy after split. Let's say if I'm trying to split or consider an outlook as root node, then I will have these features, right? For this is the entropy. What will be the information gain? So for calculating information gain, I have to know the entropy after split. So this is how we calculate entropy after split, which is nothing but average information. So this is probability of sunny. No, it's not probability. It is number of positive. This is, we have already calculated, right? Probability times entropy. It is sum of sigma of probability times entropy, which is nothing but sunny, P sunny. We have 3 values, right? So positive sunny. Positive sunny means whenever it is sunny, person will play, which is nothing but this one. Sunny play. We have 2 times, right? So that is what this positive sunny means. Plus n sunny by p plus n. This p plus n is nothing but total one. Total means this one. This 9 plus 14 we have, right? This one. Play tennis. So we are trying to find out probability of each one. Okay. And this is the total one basing on our data which we have. So this is nothing but 3 plus 2 by 9 plus 5 times of entropy when it is sunny, which is 0.971, plus similarly for rainy and overcast. This gives information gain, the average entropy after split as 0.693. Now my information gain will be entropy of yes minus this average information, which gives 0.247 as gain. This is information gain if we split or if we consider attribute as outlook. Any questions still here, or is this clear?
No, it's clear.
Okay. Similarly, what we will do, we will calculate entropy for other attributes which we have. Okay. Now, this is temperature. Let me show you. So now we are considering this feature, which is nothing but temperature. Temperature has again how many values? Hot, mild, cool. There are 3 values here. Okay. Basing on which we will find out like how many yes, how many no. Again, we'll calculate entropy similar way. And information, average information. And this information is 0.911. Okay. And we will calculate gain now. Gain is entropy before split, which is this 0.940. I mean, this is which we have calculated on the total one. You remember the first one on the whole data, basing on Platonist, minus this one, which is 0.029. Now the third one is humidity. So similar calculations actually. And humidity, and we have calculated on the other attribute, which is windy. So if you see this, right, these are the information gains here. Okay. 0.247 when we considered outlook. When we consider temperature, it is 0.029. The other one is humidity 0.152. The other one is windy. So outlook attribute has given the maximum gain. So we will consider outlook as the root node. Okay. Are we good till here?
Yep, go ahead.
Okay. So this is how our decision tree will be for now initially. So the root node is outlook, out of which we have, I mean, these branches are nothing but the values. Okay. So it has 3 values: sunny, overcast, rainy. If it is overcast, it is always yes. Person will always play. So there is only one leaf node here, which is always yes. Okay. So here it is over. Now,
Can you
have
explain that? Can you explain that? I didn't understand.
okay.
Outlook where it is overcast. Show me that.
Yeah. Overcast, it is always yes, we see.
Oh, okay. All right.
Okay.
All right.
Entropy is 0.
And can you just show me the part of the algorithm where it says how to stop? Show me that line in the algorithm where it says,
Okay.
go to the algorithm. Can you just help me? So would that
If
be if
examples
all
are all
examples are
positive,
positive? All right.
return the single node.
Okay. All right. All right. Okay. Got it.
Okay. So this is stopped here. Okay. It has only one value.
So no
Now,
more branching, is it?
yeah, no more branching in overcast.
Okay.
Okay. Now that we have to find out what will be the next node. Okay.
So question, how
Mm.
many data points move to the sunny branch? So Outlook, before you started with Outlook, there were 14 data points, correct?
Correct.
So how many move to the sunny branch?
1 minute. Sunday. Sunny, we have 5.
Okay, so 5 data points move to the sunny branch and then another 5 goes to the rainy branch, is it?
Correct.
Okay, so question. So let's just focus on one of the branches. That's sufficient because other branch will be the same logic,
Yeah.
right?
Yeah.
So let's do the sunny branch.
Hmm.
So question again. So when you repeat this algorithm, you have this P plus N and whatnot, correct?
Mm.
So when you move into a branch,
Mm.
do you still use the same 14 or do you use the one that, the number of data points that
No.
moves into that branch?
Number of data points that goes to the branch.
All right. So which means, correct me if I'm wrong. So when you look at the P's and the N's,
Mm.
where you take a decision at this, if you go down the Sunny branch, then
Mm.
P plus N would be 5. Is that right?
Correct.
Okay. All right. Got it.
Yeah.
So
We'll
it's like a recursive thing. You start at 14, you go to the next, branch,
Mm.
then you repeat the same process again and
Correct.
keep going down. Okay. Until you
Correct.
stop. Right.
Yeah.
Okay.
Correct.
Got it.
Now
Just
we have
show
to-
us the sunny bit. Okay. No need to
No.
show us the rainy bit. Just show us the
Sure.
sunny bit.
Okay. Now this is sunny bit. Okay. I'm taking the sunny bit here. We have 3 no's and 2 yes. For this entropy, I have calculated. Okay. This is 0.971. This is again P log P. P is probability here. Probability is 2 by 5, right? 2 times yes by 5. 3 times no by 2 plus 3. This is entropy of total sunny branch whenever the outlook is sunny. Okay. Similarly, we have calculated entropy for windy and this thing.
Why? I'm just curious.
Mm.
What happens if you again group by outlook?
Outlook is already taken, right?
I know,
We
but
will
let's
have
say you were
to
to group
leave
it by
that.
outlook again. What happens?
No, we have to leave that and run for other things, right?
No, I understand. But what happens if you were to do it?
Outlook again, I mean, information gain will be 0
Why?
because
You're right, but why?
we will get same entropy again because we will have the same probability, right?
You're right, but you're absolutely right. But can you just explain that in terms that we were
I mean-
using? So, okay, let me put it this way. So what was the distribution of play tennis
Mm.
when I move into the sunny branch? What's the distribution?
Play sunny branch, we have 3 no's and 2 yes.
Correct. Now let's say if I were to group it by sunny again, I mean
It
by
will be-
outlook again,
Mm.
I have just one value now for outlook. I can't because we know that once I'm into that branch, the sunny branch, I'm not going to get overcast. I'm not going to get rain, right?
Mm.
So when I try to split again by outlook, I just have one value with me, which is sunny, correct?
Mm.
So if I were to do that post split, how would the distribution look?
It will looks the same with 3 no's and 2 yes.
Exactly. So when the distribution remains the same, it goes back to the example, folks, where we did that spreadsheet, where if prior to the split, there is a certain distribution, and if after the split you get the same distribution, then there's no improvement in information. So information gain is 0, which is why by design we remove the attribute that we used for. So in this particular case, we used the outlook attribute at the root node, and we ignore it and we just focus on the other attributes. Proceed, Sarisha, go ahead.
Okay.
But okay, let me ask another question. I'll throw this to the audience.
Mhm.
Let us say, so these are all categorical variables, folks, right? All these are categorical. Let us say outlook was measured not in terms of categorical variables. Let us say it was continuous. Instead of saying sunny, rainy, whatever, let's say it was some number and it was a continuous stream of numbers. It's a continuous set of numbers, let's say. Okay. Now I'm going to ask you a question. Can I again use the same attribute as I traverse down the branch? You understood the question, folks? This was all categorical. So we knew that I start with outlook, I go down the sunny branch. And if I try to again use the outlook variable, then there's no change in distribution. Why? Because I'm going to deal with one single value, which is sunny. So it's not going to change the distribution. But let's say outlook were not to be a categorical variable and it were to be a continuous variable. And let's say the branch was something like greater than 4. I moved down a branch. Okay. My question is, if I move down a branch, and this branch, I had split that branch on the basis of outlook, and I used the following condition. If outlook is greater than 4, I move down this branch. My question is, can I use the outlook variable again now that it's continuous?
Yeah, we can use that. We can't use again the outlook is greater than 4. We can
But-
use some other numbers.
Exactly. So it could be greater than 8, between 4 and 8. Yes, you see, I've traversed down the branch where it is greater than 4. Now, of course, I'm dealing with numbers greater than 4. Now here I can split, should I want. I can use one branch where, or rather I can move into one branch where it is greater than 8 and another branch where it is between 4 and 8. Right? So this thing about not
Anyway, again, you are categorizing it again.
exactly. So this thing about not reusing the variables or the attributes down the tree is very specific for categorical variables. So when we deal with continuous variables, you can reuse
For the split.
exactly, and this is something that we will see when we do C 4.5. C 4.5 is like the mothership of decision tree algorithms. It built upon the ID3. When we do that, you'll realize how we can use continuous variables too. Sarisha, over to you. Go ahead.
Okay. So here, for outlook equal to sunny and outlook equal to rainy, right? I mean, we have calculated this entropy.
No, just go down the sunny path.
Okay.
So what are we going to deal with? We're going to deal with humidity and windy, is it? Now that
Yeah.
Okay, go ahead. And temperature too. Is that so?
Yes.
Okay, fine. So it's a repeat of the same process, right? Correct?
Yeah. Repeat of the same process.
Why didn't I see temperature in the tree? Show me that.
Okay, 1 minute. Let me show you the values. So if you see this, right? I mean, the whenever for humidity, gain is 0.971. For temperature, it is 0.571 and wind is 0.02. So the next node will be sunny. Sorry, humidity.
Okay,
The next
but
node in sunny will be humidity.
does that split the data into pure classes? When you go down the humidity normal and humidity high,
Yeah, that has split down into pure classes.
which means there's no mix anymore. Am I right?
Yes. Yeah. See, if you see
So
the
high is
sunny,
no.
height, no.
Okay. High is
Normal.
no and normal is yes. So which means the algorithm
Yes.
stops there.
Correct.
Right?
Yeah.
Okay. Show me the rainy bit now. Not the calculation, but show me the how does it okay, so where is the rainy bit? Is this rainy? Yeah, go to the rainy bit. Yeah. Okay, wonderful. So let's see. Is it sunny or rainy? Rainy. Okay. So again, 3. So you still have temperature, but windy dominated, correct?
Correct.
Okay. So when you split it by these windy attributes or other windy attribute, how does it split? Again, pure, is it?
Yes.
Can you show me that? Do you have it handy?
Yeah. I have it. Windy.
I think it's here. I can see that. The rainy. Can you just just stop there. This yeah, correct. So
Strong,
rainy,
no. Weak,
strong,
yes.
no, weak, yeah. So which means your algorithm stopped because you reached a stage where if you go down the strong path, you know that you're not going to play tennis. So there's no question of splitting any further. You go down the weak path, again, you know that you're going to play tennis. So which means there's no question of splitting further. So though we did have the attribute temperature, we never quite used it in the algorithm.
We got
right?
the leaf nodes. Yeah.
Okay, wonderful. Any questions, folks, on whatever we've done so far? I think somebody asked the question in the previous session, why is temperature missing? So we know why it is missing. right? Question. Let me post this question. Can you just stop your screen? Yeah. Thanks. So let's say hypothetically, I go down this rainy, strong path and play tennis. I mean, I didn't get this pure classification. I got one as yes and the other one as no. What next? Someone, what is your gut feel? Not the usual crowd, folks. I want someone else to answer. What next would we do? I go down the rainy, strong path, and instead of this pure classification of no, one of them turns out to be yes and the other one turns out to be no. How do you think the algorithm would proceed after this? Just go down that path. Forget everything else in the algorithm.
It will get greedy and then start using the next attribute.
Exactly. It will try to look for another attribute, correct? To see whether it can split the yes, no into two, right? It'll try to do that. Now just imagine, folks, the way ID3 algorithm works is it'll keep, unless you get this pure classification cases, it'll keep going down and down and down till it gets to a stage where it sees pure classifications. Don't you see that? If you look at all the leaves here, look at all those leaves here. They're all pure classifications. In a sense, if you take a leaf, you'll find it's either a yes. I mean, all instances are yes, or all instances are no. And if for some reason you don't see that, it'll again go down. It'll again go down till it comes to a point where it sees pure classifications. That's what it usually does. And if you think about it, and that's the whole problem with ID3 algorithm in a way, because
It's like, I won't leave you till you say yes.
exactly, correct. I will try to use as many attributes as possible till you say yes or no. Correct. And it may not be very meaningful for me. Just imagine if I do all this and if I get one yes at the end of one branch, okay? And let's say there are hundreds of branches there. In one branch, I see one yes, another branch, I see one yes, another branch, I see one no. The question is, what is the point in using all this? The whole objective of running such an algorithm is to generalize. It is to take a specific examples, which is a data set that we have, and to generalize it so that you can come up with a decision tree. It will be useful for us. But then if it throws up a complex decision tree where at the leaf you have just one data point. So let's say hypothetically, you had 40 data points. You construct a tree, a decision tree. It is so deep that at the end, at each leaf, you have one data point. Then what is the point then? Now, what is the point of using this decision tree? A decision tree will be useful when you go down a path, lot of data comes into that, branch, then it's useful. But if it's just one element in a leaf node, then it's practically useless, right? So ID3 algorithm, as it stands, I mean, at least a rudimentary one that was created, suffers from this problem because you keep going down and down and down till, as Pavitra says, you say yes. This is like the, I mean, the greedy girlfriend or the greedy boyfriend. You just keep pestering your pestering the boy or the girl until they say yes, right? That sort of thing. So, which is one fundamental problem with the ID3 algorithm. And that's where we eventually move to C4.5, where we try to see, is there a way to, do something about this? If it turns out to be too big, is there a way to make this decision tree smaller? It's called pruning. We're not going to discuss that today, but you need to understand why we do pruning. We do tree pruning because algorithms such as ID3 could lead us to a situation where you have a big tree, a lot of depth, but practically useless. We just want to avoid that. Okay. Anything else that you wish to share, Sirisha? If not,
No, that's all. This is
all
the
right.
final tree.
Wonderful. Okay. Kyle, just show us what you have.
Yes,
I
yes,
think you
let
have
me
some.
share my screen.
Yeah, please go ahead.
Is my screen visible?
Yeah, please go ahead.
So before jumping into the algorithm, I just want to explain about this node data structure. So when we are doing it manually, we can draw the tree at every step when we are getting a new node. But in the program, what we'll be doing is we'll be storing in a particular type of data structure, that is the node tree. Here, how this data structure works is it has, I've used class and it has some attributes and some methods. Let's not worry about this method. This class represents one node, the one circle or oval. Here the label represents if it's a leaf, then its name will be stored in this label. If it's an attribute, then it will be stored in the attribute. If it has some branches, some subtrees, then it will be stored in this branches of the type dictionary. And that's it about this. This is a node data structure. So yes, this is where my program starts. So here I'm importing my file and reading the Excel.
Hey, question.
Yes.
So this, as it stands, this algorithm would work irrespective of the data that you give, is it? Or is there a restriction?
SVC.
So it's very generic. So which means I can give you another data set and it'll give me the tree. Is that so?
SVC. I've also tried the rest with the same algorithm.
Okay. Wonderful. Okay, good.
So after reading it, then actually the first column will be of the name of the day 1, day 2, day 3. So we are dropping the first column, and the rest of the columns except the last one, which is the target attribute, we are leaving that and storing it in the attributes variable. And the last column will be stored in the target attribute. And we are sending all of them in the ID3 function and calling the function. The first one represents
ID3, is that a function that you created or?
SVC.
All right. Okay. So you're not using any scikit-learn function or anything of that sort, correct?
No VC.
All right. Okay, go ahead.
So this is nothing but initially when we are reading the Excel, it will be in the form of data frame. We are converting into a dictionary. To be very clear, it's a list of dictionaries. I'll show how it seems. And here we know it's target attributes, a list of attributes, and target attributes, it's play tennis. And attributes are a list of attributes. And let me show how it is. So this looks like it's a list of dictionaries. Every instance is stored as a dictionary. The first day.
Each is a data is a row in that Excel. Is that so?
Yeah, each dictionary is a row in the Excel.
All right. Okay.
And here's where our algorithm starts. Initially, we'll be creating an empty node. Right?
Yeah, you don't need to go through the algorithm. We'll leave it to the.
Okay.
Just briefly tell us, give us a high-level overview as to what this does. So this is the part that the one where Sirisha had that block, right, which talked about when to stop the algorithm and things like that. So is this that bit? I think that's how.
Yes, we see.
Your comment seems to suggest that. All right. Yeah. Okay. Go ahead.
So the first conditions is to stop when we'll have a pure attribute. Whether if it's pure yes, then we will label it as the S and we will label it as a leaf node, and it'll stop the L. stop that recursion part. And if it's a pure no, we'll be stopping there. And the next thing is, if we don't have an attributes, but still we are having combinations of yes and no means, we'll be still having some data points. From that data points, we'll be choosing whether there are most yes or most no, and we'll be setting that as the
Okay, so
leaf
just
node
to
for that.
understand, so this is a case where you go down a branch, you've used all your attributes, but then you're still not at a case where, you're still not at a case where your classifications are pure, in the sense you still have a mix of yeses and nos, correct? So there's
Yes,
no more
yes.
attribute for you to split. What do? It looks like as though we've hit a roadblock. And what you're suggesting is, in that case, we will just take an approach where we go by the majority. So if there are, say, 5 examples, I don't want to use the word example, 5 instances at that stage, and 3 of them are yes and 2 of them are no, we will say the end result is yes. Is that right? Am I getting it right?
Yes, we see.
All right. Okay.
And next we'll be having one more condition also, which is when we don't have any instance. When we'll get is to explain this, I have to use the restaurant one is actually.
Well, that's okay. That's
in
okay.
this-
Don't worry about it. But just briefly tell me what is the scenario.
Shall I show that?
No, because that'll take a while to explain. But briefly tell us just a scenario. What situation do you? Under what circumstances do you see this?
Which is when we're going down the nodes, we'll be avoiding some of the instances, right? So if you take in our tree, which is if you go below the outlook, which is in the side of rainy, we'll be avoiding the overcast and sunny instances. So if we have, let's think about, we have one more attribute in wind, like weak, strong, or something as mild. But when we are hitting the wind, we don't have any instances that have the value of mild.
Oh, all right. Okay.
So at that time, we'll be hitting the point like we don't have any instance for that particular attribute.
So what you're saying is, under wind, let's say there's a mild, but for some reason, when we went down this path, there was no data, no instances where the wind was mild, correct?
Yeah.
Okay,
right.
Got it. Okay, all right.
So at that time also, we'll be going with the most common value.
Okay.
And if none of the 4 cases were true, then we'll be trying to calculate the best attribute using our
Information gain.
Information gain. This is similar to what we are seeing using the direct formulas.
Okay. And does your code draw the tree structure eventually? Does it?
Yes, we see.
Where does it draw? Can you just show me that part where it draws the tree structure?
Yes.
Okay, so which library are you using to?
A diagraph from Graphis.
Oh, okay. All right. So at the end of it, so can you just run this whole thing and show me? So this is like what you get to see after the end of the. Are you printing the tree structure after every stage, or?
No, we see at the end only.
Okay, at the end. Okay, just scroll down, because I saw an image, a partial image of the tree. Just scroll a little above.
No, it's a different tree. I tried with a simple example.
Oh, okay. All right. Okay. Can you just sanitize this before sending it to the group, if you don't mind? Okay. So that we just see the one that is relevant for this particular tree. Okay. Just scroll down. So you run this, and then eventually it also converts that
Thanks,
into a graphical structure. Okay, wonderful. Okay, good. Lovely. So what I would recommend is just clean this up so that we see just the maybe just think about it. If you want, you can show this tree structure at each stage of the algorithm, right? Just think about it if it's possible, because visually it'll be very appealing then, right? Otherwise, this is also good. Just clean it up and exclude stuff that is not probably relevant. But this is wonderful. Okay, any questions from the audience? I know it's a bunch of code, but still. All right, if there isn't any, thank you, Kyle Vedi. Any questions on ID3 so far? Okay, as always, I shall take silence as no questions. Thank you and have a good evening.
Thank you.
Thank you. Bye.